Okay, great. All right. Hello, everyone. Thank you for finding the time to tune into today's installment of the Corundum developer meeting. So let's go ahead and get into it. All right. So I've got announcements and status updates. So announcements, the next developer meeting will be on April 2nd, 9 a.m. And for people interested in the Switch development with Carlos, the next meeting for that will be next week, March 12th. I guess Carlos couldn't join us today, but um, hopefully we'll have some good stuff next week to talk about. All right. So moving on to the status updates. So I've gone ahead and put up deprecation notices on a bunch of the old Verilog repositories since stuff is now being migrated over to System Verilog. And I've also been, like I said, working on the System Verilog migration. So I'm going to talk a little bit about where things stand with respect to that. I also put together new MAC-PHY and GT wrappers for Xilinx devices, so I've got a couple details on that because I think all of the new development work that I'm going to do relating to the transceivers that's going to take place in those new wrappers. Um, I also have been doing some more work on the DDMTD um, demo stuff, and that dovetails with the consistent latency transceiver configuration stuff, which is going to be necessary for actually implementing something like White Rabbit. Like previously with the demo, I just ran it with the asynchronous gearbox, and it works well enough until you reset it, and then you have you can rolling the dice on a new latency basically every time that brings up the link. So obviously that doesn't work in the long term for something like White Rabbit where you need the latency to be consistent. So I've been looking at the documentation and I'm putting together a test design to try to nail down exactly the right way to configure the transceivers for not necessarily low latency, but consistent latency. Although those sorts of things tend to go hand in hand. So we'll see how that pans out. All right. So, like a first thing, deprecations. I've added deprecation notices to a bunch of the old permissively licensed code, the Verilog Ethernet, AXI, AXI Stream, all that stuff. I think there's a couple that I haven't added one yet, but it's all effectively deprecated at this point. All of those repositories will be superseded by the new taxi repository. So I've been um, transferring the code over bit by bit and updating it for System Verilog with new System Verilog interfaces, and the new um, always blocks, always FF, always COM, whatnot to get stuff cleaned up. I'm not going to be doing any further development or support for the old permissively licensed code. And this is, I suppose, one of these good news, bad news sort of things. Bad news, no more support for the old code. The good news is that if you do want to see, if you do want to use, this code in a commercial application and you want it to be available in the long term, the easiest way to do that is to license it. If you guys are paying my salary effectively, then I'll be working on this, as long as I possibly can. I also want to be perfectly clear that the terms and the rates are going to be negotiable on this sort of stuff, and I'll do what I can to help people move over to the new System Verilog code base as well, if you're interested in licensing it anyway. It's not going to be like Xilinx where it's like, oh, 50K for a Mac. You know, that's either you pay it or that's it. I'll work with you to find solutions that are appropriate for whatever it is that you're doing. Right. So moving on to the System Verilog rewrite itself. The long-term plan is to rewrite Corundum and all the libraries in System Verilog and to switch to the CERN OHL strongly reciprocal license. So to that end, I'm starting with all of the libraries because without the building blocks, it's kind of hard to port Corundum itself. So I have a new taxi transport library that's up on GitHub. And I have System Verilog interfaces for AXI, AXI Stream, and AXI Lite. All that's up there right now. And I've been porting the core library modules piece by piece. So I have probably right now most of the AXI Stream stuff ported. I've got a lot of the Ethernet MAC level stuff ported, um, and a few other things, some details on the next slide I'll get to in a minute. I also have the new transceiver wrappers that I put together and example designs using these wrappers as well as a couple of the other components on a bunch of different boards. Right now, only Xilinx boards. I need to basically build new wrappers for the Intel boards as well, but one step at a time. Um, so just as a little refresher on the tooling status, um, with the Verilog versions, I've been using Icarus Verilog with for system Verilog. Unfortunately, Icarus Verilog is currently not usable because it doesn't support mod ports. Like you can create interfaces, but you can't use them, which is kind of weird. But anyway, maybe they'll fix that at some point. Until then, at least Verilator is seems to be a good option because it works with Coco TV and the system Verilog interfaces also work, and it also has a linter, which is while rather pedantic and slightly annoying at times, I think it definitely is going to help reduce the potential for bugs. So I think as of right now, all of the code that I've been pushing up into the repository, um, I have the linter, fully enabled. There's a couple of places where I've had to, um, piecemeal disable a particular check, but for the most part, the linter is fully active. So um, that's definitely fixed a few things. In Vivado, I've been using Vivado 2021.2. I've not tested it with the latest version, but I assume that if whatever I'm doing works in 2021.2, it should work in most everything since then, unless they've added new bugs, which is entirely possible. Quartus, I've done test builds in Quartus Prime Pro 23.1. It does not currently build in Quartus Prime Lite/Standard because they have a very old System Verilog version. But I have been working with SV2V in trying to work around some of these problems, and we've I've gotten a couple of bugs in SV2V fixed already, but there's still um, a couple issues that need to be sorted out. And I think now at this point we're not necessarily talking about bugs in SV2V and more about issues in terms of how Quartus and or ISE are interpreting the code and certain constructs that they don't like. So it's a question of, I mean, for ISE, I don't know if there's much that can be done about that or if it's even worth the effort. For the Quartus problems, some of this could potentially be fixable if we get Intel involved, or we figure out how to make some modifications to SV2V to avoid generating some of this problematic code. But it seems like there is the potential for being able to build, at least in Quartus Prime Lite and Standard, with SV2V. I don't know about ISE because of some of the constructs that are problematic there. But yeah, ideally I would like to be able to keep the hardware support for all of the different device um, series, all the different device families that were available in the older Verilog Ethernet repositories and whatnot. But um, we'll see about that. And if SV2V provides the path for that, then that could be a pretty good option. Um, all right, that's the other thing to just touch on briefly is the kind of improvement that you can get with the interfaces in System Verilog versus connecting stuff up directly with wires. So this is what you have to do in Verilog if you want to instantiate one of the AXI stream adapters. You have to connect a whole bunch of parameters to indicate the widths of all the signals, and then you also need to connect all the signals. And I suppose this is only part of the picture because you also have to declare all of these signals and all these parameters somewhere, and then they also have to be connected to, another module somewhere else. So the full code to do this, um, you figure is probably at least twice to, two times or two and a half times something what I have listed here. But with System Verilog, well, first you have to define the interface, right? And that basically takes the same number of lines here because you connect all of the parameters to that. And then when you actually instantiate the module, it's just one line for the input, one line for the output. So not only is this saving the amount of code that you have to type and manage, but it also is reducing the potential for errors because I've definitely messed things up in terms of hooking up parameters and individual signals before, and those errors can be very annoying to track down. So by bundling everything together, that's, I think, going to be a significant advantage going forward for just making sure that that things are actually connected properly um, from the beginning instead of having to do a lot of debugging of, is this, why is this particular parameter getting this value that doesn't make any sense? Oh, there's a typo. Yeah. I mean, that can still happen, but it reduces the footprint. It's the same kind of reason that higher level programming languages can use object oriented structures and whatnot. It reduces the chance for some of these types of bugs. Um, so moving on to the porting progress. Let's see. So most of the AXI stream library has been ported. I've been also piecemeal porting some of the AXI code as well. I think right now I have like the RAMs and some of the register slices. Haven't done the crossbars yet. I'm working on that. Um, I've got the tri-mode Ethernet Max ported, so RGMII and GMII, as well as the bare Mac that you can connect to the SGMII core. I've got the 10 gig and 25 gig Macs ported over, including the combined Mac and Phi module at 64 bits. I've got the PTP logic ported over, the LFSR logic ported over and updated for System Verilog. Um, let's see. There was a change that I had to make to the LFSR module that significantly improved the. Yeah, I guess I did an overhaul of the LFSR module. So previously with the Verilog version, um, I didn't have it written in a very efficient way, and as a result, it was generating a very, very large amount of C++ code in when you run it through Verilator. And part of the reason for that was just the limitations of Verilog, where you can't pass around multi-dimensional arrays, but with System Verilog you can. So I was able to rework some of that and simplify it. So now it simulates better. It doesn't take nearly as long to compile, which is nice. Um, and I also have the UART code ported over as well. For the short term to do for stuff to port, basically the rest of the AXI Lite code, including crossbars, adapters, and the DMA components. Um, I squared C is mostly ported. There's a couple straggling things I need to sort out to get that done. I'm also going to port over the XFCP code as well, so that can be used in the example designs and for some of the experimentation work that I'm looking at. PCI Express is also going to be ported over as well. I was thinking about doing a pretty significant rewrite of that, but I think what I might do is port it more or less as is first, and then do the rewrite kind of in parallel, so we can have something working first. And then I'm also putting together synchronization primitives instead of the sort of ad hoc synchronization that I had previously. So I got to write a few more modules for that, but the idea is that this should reduce the need for a bunch of additional timing constraints files um, and just streamline all of the synchronization. So, if you need a pulse sync, you just drop down the module instead of what I was doing previously, of just ad hoc writing a pulse synchronizer when I needed one, which, yeah, there's been a few modules I've updated already. I think mainly I've been installing the reset synchronizer module in a bunch of other places. So that'll make things a little bit easier to work with. Um, long term is to port the UDP stack. There's a number of things that I want to rework about how that stack is set up, including getting it properly parameterized. Because right now it isn't. So that's going to be a longer term to do. If somebody is interested in, using and licensing the UDP stack, I might be able to, shuffle things around and get that working more quickly. Please contact me if that's something that you're interested in. Otherwise, it might be a while. Moving on to the example designs. So, in the interests of, maintainability, what I want to do is have like a single example design for each board. That's sort of a kitchen sink design that brings up, a whole bunch of different peripherals. So, PCI Express, Ethernet, DRAM, just whatever is on the board that makes sense to connect just to bring it up. So the current ones, they light up the Ethernet ports and the UARTs. Once some of the AXI code is, more complete, I'll probably add some AXI infrastructure stuff and turn on the DRAM interfaces on whatever board. The the way the Ethernet ports are hooked up right now, it's not the UDP stack. So testing it with something like Netcat, I mean, I guess technically it probably works, but it's not super optimal. But it works great with the network tester like the Viavi ONT or the 5800. So for all the example designs, I've tested that with back-to-back minimum length frames, and everything looks good. Um, but yeah, eventually the idea will be to have some additional options potentially configurable through dip switches or something that will let you test other stuff as well as just a very low level loopback. Bunch of to-do items here. I need to support Intel parts and boards that need I2C or MDIO bring up. So, those like big high-tech level boards, you need to configure the clocking infrastructure on those via I2C. The VC1AT needs some MDIO stuff in order to work properly. So that sort of stuff, that's going to be a to-do once I get the MDIO and I2C code ported over. I also want to add support for a couple different FMC boards. I've got like the High-Tech Global 6X QSFP28 and 10X SFP Plus on at least a couple of boards. I mean, there's a lot of boards that don't have FMC connectors in the first place, but yeah, at least for some of the larger dev boards, it would be useful to have that. Um, like in the old Verilog Ethernet code, I think for a couple different boards, I had example designs, including the QSFP28 board. So I'll be bringing those back as well. Again, once I have I2C working, at least for the QSFP28 board. Right, so that's the example designs. The other thing that I've been working on is the new Mac Phi GT wrapper. Um, so this one, so previously I had a Phi plus GT wrapper. So what I decided is going to make the most sense here is to add the Mac as well, but then kind of repack it and configure it such that it can be run inside of the core instead of as a separate module at the edge, which means that you can get better integration testing, right? Not just the data path itself, but also some of the sideband control stuff, statistics, timing, um, transceiver control and status registers, that sort of thing. And the idea is that this is going to be built with more modular design practices and CDC primitives to make it easier to deal with. And so far, I have a relatively basic version of this running that's more or less just the wrapper that was used previously in the example designs. What I need to do is port over some of the higher level stuff that I have in the wrapper in Corundum. I also need to make similar wrappers for Intel parts and support. The idea is I also want to be able to support 1 gig and 100 gig, so you can do auto negotiation from 1 gig all the way up to 100 gig. And by 100 gig, I'm talking about including the CMAC inside of the wrapper as well. Would be useful to support auto negotiation and then also to integrate statistics collection and the high resolution timestamping functionality as well, all into the same wrapper. So you can just drop that down, hook it up, and then you get all these capabilities. So now that the wrapper is there, I can start adding this functionality to it. And again, it's in all the example designs. So you'll be able to test this out in all the example designs for whatever, if there's a board, if there's a design for the board that you're using, then you can try it out. All right. So moving on to the high precision timing stuff. Like I mentioned at the last meeting, I updated the 10G synchronous Ethernet demo setup for the PTTI conference, and basically I figured out why I was getting not so great performance with the GuideTech time measurement cards, and that is the fact that the slew rate coming out of the pin I was using to try to measure the timing was too slow, and basically as a result you get noise when you try to sample that on the time measurement card. But if you look at the phase detector inside, you get a much better reading of the true sync performance. And with everything all tuned up, this seems to be able to measure a 10 picosecond step, or even better than that, with the optical delay line. So this is what the setup looks like that I put together for PTTI. So we got the optical delay line hooked up to two U200 FPGAs, and then this is what the output is with a little simple test program I put together, which steps the delay line 0, -10, 0, -9, 0, -8, so on and so forth, all the way up to +10. And you could see, with a little bit of averaging, you can pick out even step sizes of just a couple of picoseconds here. So the idea is to continue to develop this, effectively demo into something that is actually capable of working with White Rabbit. And so this demo was done at 10G with the asynchronous gearbox. The idea is to move the transceivers to a configuration that has a much more consistent latency. Like I said, we're looking at consistent latency, not necessarily low latency, although they tend to come hand in hand. To get consistent latency, the general method is to bypass transceiver components that have non-deterministic latency. So where do you get non-deterministic latency? Well, if you have a clock domain crossing, obviously characterizing the latency of that is going to be difficult. So in the transceivers, there's the asynchronous gearbox that has CDC in it, and there's also the TX and RX buffers, which I think are less about crossing between different clock frequencies and more about dealing with different clock phases. And while different clock phases, it's also going to be variation in latency, especially when you're talking about, fractional clock period stuff, sub-nanosecond stuff. The clock divider state and the serializer state is another potential component for transceiver latency, although there's less that can be done about this directly, and more about, this is just something that has to be compensated for as long as you can track what that state actually is. And then also the gearbox state as well, which is going to, now this is, I guess there's two components to this, right? With the async gearbox, you have a CDC, which is a problem. But then the gearbox latency will also vary over time. And you can't necessarily compensate, or you can't necessarily remove that latency. But for timing applications, as long as you know what it is at any given point, then you can compensate for it. So first pass, what I'm doing is assembling a test design with transceivers in various configurations and with DDMTD logic to measure the phase. And I'm going to look at several different modes, right? So I'm going to put the transceivers into TX and RX buffer bypass with no gearbox, and then test 1 gig, a couple of 10 gig configurations, and 25 gig. And the basic idea that I've come up with is to send not exactly PRBS data, but sort of something that looks kind of like the 6466 encoding, where you have a fixed 0, 1, and then, n-2 bits of PRBS. And then with that, you'll be able to see what where the CDR locked, basically, right? Because you have, for a 64-bit interface, you've got 64 potential barrel shifts that you could end up at. So the idea is that you can see that very easily by looking for this little sync header at every possible position. And then you can also measure the phase with the DDMTD, and you can compare those and make sure that after resetting the transceiver or interrupting the link hundreds of times, you're getting consistent results. And if that works, then that indicates that that particular transceiver configuration should work. And then the next step is to modify the PCS and MAC logic that sits on top of the transceiver to support using the transceiver in this mode. So I'm working on putting that design together right now. I've had to port some of the XFCP components in order to actually talk to this, because this is not, I'm not building this on top of Corundum. I'm just doing, bare transceivers for the time being. And then later on, we'll roll this into the wrappers and integrate it into Corundum. So hopefully I'll have more news on this in the next meeting when I actually get the thing working. So yeah,
Alex here, familiar
yeah.
with I know that it's the group at CERN, or one of the groups at CERN, I don't know who
Mm-hmm.
has done, so this is, they do something about like resetting the transceivers over and over. Is this the same thing
Yeah,
or?
I've heard about that. Yeah,
Okay.
So I'm not sure exactly what problems that they're running into there. I mean, I'm sort of trying to repeat that work as well, and also come up with a way to do this for other devices, right? It seems like every FPGA family are probably going to have to do similar characterization to figure out how to configure the transceivers. So, um, yeah, I've heard that they've had to play some weird tricks to make things work. And I guess that's part of it is that, while you can reset transceivers multiple times until you get the latency you want, you also have a way of, characterizing that, right? You have
Right.
to have a way of knowing when you've actually hit the value that you want. Um, but yeah,
I
that's
I was just making sure you were aware that of that. I don't know the
right.
detail.
Yeah. Well, so the other thing too is that, you know, the White Rabbit stuff, they've been doing that for a while on several different FPGA families. So it's possible that on some of the older FPGAs, they've had to sort of play roulette or something like that with the receivers in order to try to get the right latency value. It's possible the newer ones are better behaved. I'm not sure. But yeah,
Yeah, I guess
my
the
guess
the
is I'll probably load it on the board and then realize, oh, there's something funky going on here, and then have to pull out the ILA and see if I can sort it out. We'll see.
I
Uh,
think that if you want to look for the term, it's Tom's Casino that does the resets and then tests for the right delay, I guess.
okay, okay.
So if you want to
And
have a look at it. But I guess you are right, newer transceivers are better in reporting the actual state rather than you need to kind of randomly force them into a specific one.
right, right, yeah. Well, I mean, I think a large part is just bypassing parts of the transceiver that could potentially be a problem, right? Like the async gearbox, that's not going to work. So you bypass it. But yeah, it's like, okay, once you bypassed everything that you can bypass, then the question is it going to do what you want? Um, and yeah, we'll see about that, I guess. Um, but yeah, so that's in their current code base on
Yeah, I think so. Yeah.
well, I guess I can look that up. Can look that up later. I did a while ago look at like their DDMTD implementation and whatnot just to get my head wrapped around how it works because they do kind of describe it in the paper, but you got to look at the actual implementation to really fully understand some of this stuff. Um, but yeah, okay, I'll take a look at that. Well, I mean, you guys implemented some flavor of White Rabbit on some boards over there, right? I mean, you guys have mainly been looking at some of the clocking infrastructure associated with that. Um, did you guys
Yeah,
have
right.
to deal with the transceiver resets in order to make that work, or maybe this was something you
Oscar, I don't know. Please correct me if I'm wrong. I think we didn't actually modify that, but basically took what they had in place already and we migrated from the existing GTH stuff to the GTY transceiver stuff, but it was very, very similar.
gotcha?
Yeah,
Okay,
exactly.
yeah, that was my understanding. That GTH and GTY is they're pretty straightforward. So the GTY is sort of just an evolution of the GTH. So a lot of the internal stuff is quite similar, and the behavior is quite similar. Um, But yeah, some of the older transceivers has a different story, right? You go back to GTX or GTP or something, and then it's things are looking quite different. Anyway, that rounds it out in terms of the status update slides that I have. So if people have any questions or comments, feel free to fire away.
Okay, can I ask you something?
Yeah, all right.
Uh, so I was playing with design recently, and I wanted to have like I had some questions. So in the in the Corundum design, right, when we are
Mm-hmm.
initializing CMAC IP,
Yeah.
uh, so you you enabled TX flow control, RX flow control, and also enabled RSFEC.
Yeah.
So I wanted to know, is there any point in time you needed that, or like you saw some frames getting corrupted on the path, or
Oh, the
some weird
RS
behavior?
spec. So what I determined is that some NICs don't want to bring up links when RSFEC is not enabled. So when I first started messing around with 100 gig stuff, you got to plug in something at the other end. So I'm like, hey, let me plug into a Mellanox NIC and see what happens. Plugged it in, no link. Shoot, why am I not getting a link? Eventually, I realized that I had to turn on RSFEC, and then the link worked. So at least with Mellanox NICs, they're not smart enough to bring up a 100 gig link without RSFEC enabled. Now, I don't know if maybe there's a way you can force it to bring up a link with RSFEC enabled, and some, Tor switches and whatnot don't support RSFEC at all, so you got to disable it for those. But it seems like there's definitely a good number of devices that need that RSFEC support enabled.
Yeah, we can
So
definitely second that. So we have a Dell switch that also requires it, and there's also the case for 25G links as well. So not just 100G, but
that's
all the
interesting.
25G line rates.
Yeah. I mean, the thing with the CMAC as well is that the RSFEC support is already there, so you might as well turn it on if you know, if you need it, right? It's like in my case for the 25 gig max, if I wanted to use RSFEC there, I'd have to implement RSFEC. And yeah, that that would be a bit of a pain because I'm less
Right.
familiar with the internals of how to actually make that work. Um, so yeah,
But
for to do RSFEC at 25 gig, it would be a huge pain in the butt. But to do RSFEC at 100 gig with the CMAC, it's just you pull a couple of pins and then it's on. So
Yeah, you can
but
always
I
force the link partner to not use the FEC, but you really need to do this. That's not automatically done usually. So also for Mellanox cards, we use some ETH tool fiddling to turn that off. And on the Dell side, there's also some commands for that as well.
oh, okay. So the Dell doesn't actually require it. You just need to poke it correctly. Yeah, that's one thing I've noticed with
Yes.
switches is that they tend to not really do much on a negotiation. You kind of got to force the port into the right rate. I mean, with the exception of the, tri-mode stuff. Generally, you have to manually set the settings that you need. Um, that maybe that's not universally the case, but that's definitely been my experience, right? If you have a port that's configured for 100 gig and you plug a 10 gig breakout cable into there, you won't get anything out of the breakout unless you go flip the port into the lower rate. Even on just the first lane, like you plug a 10G breakout into a Mellanox NIC, and I mean, yeah, only the first link works, but you can just plug it into something, it'll figure it out. The Mellanox NICs are quite good at figuring out what rate the link partner is, but apparently they can't figure out FEC versus no FEC. I don't know why. At least for 100 gig, and for 25 gig, they're fine coming up with no FEC. At least as far as I remember. Now I have had issues with that auto negotiation process causing problems on the FPGA end. Like there was some FPGA boards maybe with like the GTH transceivers or something, if I plug that into a Mellanox NIC, that supports 100 gig, I wouldn't consistently get a link. But if I plugged it into a 10 gig only Intel NIC, it worked just fine. And I think the transceiver watchdog stuff that I've added has improved that situation, but I'm not 100% sure. Like basically the NIC trying to run the link at 25 gig for a while got the transceiver screwed up on the FPGA, and then had to be reset to actually bring up the link. So I think that works better now. I should do another test and double check. But yeah, why do you ask? Are you just wondering? Do you want to
so
disable it for
so
some reason?
so apparently, so I was fiddling around with I mentioned that in the previous meeting. I was working with libTPA, which is just basically a TCP stack over DPTK,
Yeah.
and we were running on some issues. I now the problem is on one end I have DPTK, on the other end I have FPGA. Nowhere to look at, no monitoring whatsoever. right? Also, the trace on the DPDK was like bare minimum, though it was not useful at all. So no idea why like some packet was getting dropped. So I looked into the CMAC configuration in my design, and apparently the FEC was disabled, and also flow controls were disabled, like it zeroed out both RX and TX. And but eventually it worked out. The buffers on the memory pool buffers were small, so the DPDK was dropping the packets. I cannot fit this with packet response or something.
Oh, so it actually wasn't the CMAC that was the
Yeah,
problem.
yeah, it wasn't. So, but then I thought I'll ask you, did you run into some kind of issues on the wire, or it always worked fine?
Yeah, I mean, you see packet drops all the time. I always just attribute that to the, Linux TCP stack not being able to keep up with the line rate all the time. So, well, I mean, I guess you don't really see it all the time, but it's pretty regular. You'll see a few drops here and there. Um, but I think that's sort of characteristic to the Linux networking stack when you're trying to run at high link rates, is that it's not the most efficient stack ever, right? If you want to run it at full bore, minimum length frames or whatever, you need DPDK or something, right? That's actually designed to handle that. Um, but yeah, I don't think I've seen any issues in terms of FEC on the in terms of packet drops due to signal integrity that would be correctable with FEC, at least at 100 gig.
Mm-hmm.
I mean, the thing is, right? Corundum was developed for this networking research that we were doing at UCSD, and we don't actually use 100 gig for that research, right? That's all 10 gig and 25 gig. And because we're switching stuff optically, the we actually do not want FEC enabled because it takes quite some time for the FEC to achieve lock, right? To get the right alignment and such. Because the thing is, none of this stuff is designed to bring the link up quickly, right? So this is
Mm-hmm.
something that I actually, if you look at our latest paper, I have a whole um, appendix talking about like what do you need to do to bring up a link quickly. And 10 gig, 25 gig ends up being kind of a sweet spot because as soon as you go past that, then you start requiring FEC and requiring, much more complicated equalization techniques. Um, and you use multiple lanes that need to be de-skewed and things like that, and all of this stuff, it takes a lot of time to get everything aligned and synchronized and such, right? Like the FEC blocks are like, how big are these things? They're like several thousand bits, and the way that the FEC block lock is usually achieved is they'll check to see if they're getting valid FEC blocks. If they aren't, they'll slip one bit and then they'll try again. So every time you want to check that, you got to receive at least several FEC blocks. So you got to receive a few thousand bits. And then you slip by one bit. So you got to do this whole process several thousand times in order to actually achieve alignment. You multiply it out, even at 100 gig, it takes a while.
Mm-hmm.
And, we can't tolerate that in the optical, with the optical switches because we're trying to switch the links very quickly. So if we have to wait,
Mm-hmm.
many milliseconds when our switch switches in microseconds, that's a problem. Um, yeah, and potentially you could do better if you built your own FEC implementation. But you can't touch the 100 gig implementation in the CMAC, and we weren't using the CMAC anyway.
Mm-hmm.
And at
Oh, okay.
25 gig, we'd have to build our own FEC implementation, and we just didn't have time for that basically. So yeah, so 10 gig, 25 gig, where we did care about the latency, we didn't implement FEC, and then for the 100 gig stuff, in order to make it work with the Mellanox NICs without having to futz around with ETH-tool, we enabled it because that seemed to make sense.
Mm-hmm.
It seems like for 100 gig devices, having FEC enabled by default is sort of a more sane default than disabling it by default.
Mm-hmm. Also, you enabled timestamping. So, is it packets getting stamped in CMAC, or what
Yeah.
is happening there? Okay.
Well, yeah, it's pretty common for the Macs you provide in the TX and RX reference clock or TX and RX clock domains the just free running, monotonic counter that you're going to use for
Mm-hmm.
timestamping, and then basically the Mac will just capture that during transmission and reception, and then return the value. So yeah, that's done internal to the CMAC. So we're using that capability because you need that for PTP, right? So
Mm-hmm.
yeah, and for if you wanted to do White Rabbits at 100 gig, I'm not sure how that would work. That's something that I've been trying to figure out is the best way to implement something like that if you want to do really precise timing, because then it really gets down into the details of exactly how you're capturing the timestamp and how you're um, generating those reference clocks that you're capturing the timestamp with respect to. Um, so it's one thing if you have a fully soft Mac and PCS to do all that. It's a totally different story if you're using something like the Xilinx CMAC, where
Mm-hmm.
a lot of that detail is abstracted away in some sense. So
Mm-hmm.
yeah, I'm not sure necessarily the quote unquote best way of handling that at the moment, but
Mm-hmm.
yeah, at some point I'll have to cross that bridge and probably, well, we'll see. I got to get it working at the lower link rates first before looking at 100 gig. But yeah, I suspect I'm going to have to look at some stuff on the transceiver side as well in order to actually make that work. It's the question of what.
Also, at some point in the switch meeting, we were discussing like kind of configuring a port to different link rates.
Right.
Uh, and I saw a DRP port. They name it as DRP. I think it's dynamic
Yeah.
reconfiguration port, which I
Yeah.
don't think it's dynamic reconfiguration port. I think it's just a port where you send some values and it has some internal registers or something,
Oh,
and
you
you
mean
just
on the
look
CMAC
at it.
or
Yeah, yeah, CMAX.
yeah. Yeah, so the
So
CMAC
I'm not
has
sure
a
how. Yeah.
was what we're going to say you're not
I'm
sure
not,
what?
I'm not sure how far of what all and how far you can configure things.
On the CMAC, there's not all that much you can configure via the DRP port. Um, you can change a bunch of stuff that is more like sort of diagnostic stuff. Like, so for 100 gig Ethernet, it uses multiple virtual lanes. There's like 20 virtual lanes, and each of those lanes has a lane, has a unique alignment marker. That's what it's called, alignment marker. Um, and you can change those alignment markers via the DRP. Why would you want to? But you can. um, and there's a few other things you can change, like there's a whole bunch of just ports as well. So I would need to look at the documentation. You can't change anything about the transceivers via the DRP port,
Mm.
but there's a number of internal settings in the CMAC that you can change. Um, if you do want to change the link rates, that's a potentially more complicated operation. Right now I have some software that supports reconfiguring like GTY transceivers between 10 gig and 25 gig, and that uses a DRP port, but it also has to change a bunch of other signal settings that are driving some of the ports just directly on the transceivers. And basically, what I've done is I've kind of extended the address space available on the DRP port to support changing some of these settings as well. So everything can be done via DRP. But yeah, so with that, you can switch between 10 gig and 25 gig at runtime. But yeah, long-term goal is to extend that so you can do 1, 10, 25, 100.
Mm-hmm.
And switching between 1 gig and 10 gig 25, how I'm going to do that kind of remains to be seen. Ideally, I want to do this oversampled thing, but we'll see if that works. If it doesn't work, then I got to go back to the drawing board. But if it does work, then that actually, I think, might not require reconfiguring the transceiver itself. That's going to be purely on the data path side. But I also want to be able to support switching from 100 gig down to 10 gig, 25 gig. And that involves, do we use the CMAC or do we use soft 10 gig, 25 gig max? And that will
Mm-hmm.
require some transceiver configuration because it's 80 bits versus 64 bits or whatever. So, but
Mm-hmm.
yeah, that also involves configuring both the transceiver as well as the logic sitting behind it. So a lot of the stuff I have kind of some nebulous plans for how it should be done. But now that I have the new transceiver wrappers, I can start chipping away at that. So I can test it out. The transceiver wrappers plus XFCP to read status information and poke at um, some of the DRP register settings and whatnot. And with that, we can test the wrapper and make sure everything works before we integrate it into Corundum. And then also it'll be hopefully usable as a standalone thing, right? So it's like, this is the way it's set up with Corundum right now. You can't really reconfigure the rate without having the PCI Express interface working and the driver working, and then the user space code that talks to the transceivers through all of this stuff. But the idea is to roll this reconfiguration logic into the wrapper such that, the wrapper can kind of figure itself out. And I think we're going to have some auto negotiation logic in there, but I'm not sure exactly what it's going to look like at this point. I mean, in large part, a lot of this stuff is kind of to support the switch project, where if we have these much more configurable wrappers, we can just drop that into the switch, and then we get the multiple link rates and stuff support on the switch without a lot of additional difficulty. And then we can reuse it with the NIC as well. Because if it was just for the NIC, then it's like, well, maybe we can do more in soft cores or whatever. But for something like the switch, okay, maybe it makes sense to spend a couple of more, LUTs and make it more self-contained. Oh, and I know
By
you
the
were
way, I
working on
ordered.
some sort of a packet capture thing. Did you get all the pieces for that, or?
Yeah, I ordered, but apparently too much time. I think it will arrive by the end of April.
Oh man.
And I ordered that day when we talked, when we discussed all that. I just ordered that day itself, but it is going to take
Dang.
some time.
Okay, that's okay.
But
Well,
but but
hopefully,
but anyways, like I'm looking at it for a longer time, a thing, because at some point I would want to look what is happening on the wire at the
oh
top.
yeah, definitely. No, having that capability is going to be super useful.
Yeah. But I was
Yeah.
also kind of playing with a Tofino 2 switch, uh, which it's unbelievable, right? When you have a switch which has 32 ports and 400 gig per port,
That's a lot of data. That's a heck of a lot of
yeah,
data.
yeah,
Yeah.
yeah.
Do you have
And then
NICs
at
to
some
hook
point
up
I
to that
was,
at 400 gig or?
no, 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 no. And just for now, currently, because I wanted an experimental switch totally separate from the storage node and whatnot, because we were in a situation where we are also doing a lot of data syncing to the switch, and also the FPGA and NIC experimentation was also happening through the same switch. Although I had some VLAN configured, but still I never trusted it. So kind
Right.
of wanted a physically different switch and physically different NICs for the experimentation.
Yeah, that makes sense. Yeah. Yeah, so far I have one 400 gig NIC. This is one of the Mellanox
Oh,
Connect X7 ones with an OSFP.
right,
So
right, right. We discussed about it.
yeah, I
But
do
but
need to
then my
get.
question is how many CPU cores you need in order to saturate that bandwidth? Must
Yeah, I
be
don't
really,
know. I don't
really.
know. So this is one thing I've been scratching my head over. I think I need to get another somewhat high-end dev machine and another one of these. I have a couple of the optical modules, but I need another NIC and another, machine to put it in. Because yeah, if we're gonna do anything at 400 gig, it's one thing to have the NIC and be able to bring up the link. It's another thing to actually, saturate the
Yeah,
link
yeah, yeah.
and actually utilize it. Um,
And I don't know how does the latency look like? Like, is it
at 400 gig, I don't know.
okay?
I've only so the only testing that I've done with this so far is I got, what was it? The transceiver that I got for it is a uh, it's a QSFP 1310 400 gig. I guess this doesn't really say. I think it's FR4. So it's got 4 lanes at 100 gig per lane. And it turns out it's actually compatible with these 100 gig, 100 gig FR transceivers. So this little setup I put together for testing purposes, I've got the 400 gig module here, the OSFP, and then I've got a 100 gig FR4 module, and that worked. I've also tested
Okay.
it with did I test it with a 10 gig module? Can't remember. I should probably do that and see if it'll work at 10 gig, 25 gig. Can't remember if I tried that, but yeah, so that worked. So I'm like, all right, that gives me some confidence that the NIC actually works and the transceiver actually works. But
Right.
yeah, the longer term thing is I got to get another one of these, and then I got. I thought I got another transceiver as well. Oh, I got a pair of multi-mode transceivers, the
So
SR4. But yeah, I don't have anything to plug them into, so.
we are talking about 100 gig full duplex, right? So when you say one per lane 100G, you mean 2 lanes, right? Or how many, like, what's it
Well,
has to be RX
by
and TX
lane,
lane.
it's implied there's a transmit and a
Right,
receive.
right.
Yeah.
Right.
Like for PCIe, right? 16 lanes of
Mm-hmm.
PCIe is, well, or at
Mm-hmm.
least a by 16 PCIe, you can consider it 16 lanes, but you get 16 up and 16 down, right? Same kind of thing with these.
Mm-hmm.
So the OSFP, so the interesting thing is OSFP, the O is for octal, right? So it should support 8, but in this case they're only using 4. So yeah, 4TX and 4RX, 100 gig per lane. And I guess it's a 56 gigabaud PAM4 that they're using
Mm-hmm.
per lane. So it's pretty zippy. Yeah.
Right. Yeah, at some point I inserted a QSFP28 cable on that 400G port, and I was thinking, should I have used breakout cable, or can I break it out in the switch itself? But eventually I broke it out in the switch itself, and I was then
Mm-hmm.
figuring it out how it decides the lanes, right? But then it seems like the switch supports multiple configurations, they call,
Yep.
depending on how they divide the lanes and whatnot.
Yep. Yeah. So I was actually, is that QSFP DDs in the switch?
Yeah. It's QSFP DD.
Yeah. So somebody asked me a while ago about how to bring up a QSFP DD. So I was looking at the standard going, what the hell is going on with this thing? Because it is very complicated. Because there's so many different configurations that are supported, right? Because you take a QSFP DD that has like 4 optical lanes and 8 electrical lanes. There's multiple ways you can connect those two together, right? You could take 8
Mm-hmm.
electrical lanes into 4 optical lanes as a single 400 gig link. You could take that
Mm-hmm.
as 200 gig links, as 4 100 gig links, as some combination of the two. So yeah, they have a pretty complicated mechanism for specifying, what grouping of lanes you want to use for, what protocol on either end of the
Right.
device.
Right.
Because you got to do things differently depending on, the PCS layer has to be configured differently depending on what protocols you're using. So yeah, it doesn't
Yeah.
surprise me on the Switch if it has to be able to support all that, especially if the Switch has to be able to support different modules, right? You put a QSFP DD in there, it's going to do one
Yeah.
thing, versus put a
I was
QSFP in there, it's
yeah
going to be a little bit different.
yeah I
Because
was
obviously you can only
thinking
use half the
that
lane.
whether I was thinking whether I would be able to pull it back. That was my main concern. Because at some point we discussed about it, right? You remember,
Yeah.
you told me that, okay, you put a connector into a different look-alike connector, female port, and you were not able to pull it back. But I remember it was different, right?
Oh
It
yeah.
was
Well, that
SF.
was a that was that was the CFP port on my network
Yeah,
tester.
yeah,
Because the module was not designed correctly and it had a little groove in a bad spot. So
yeah.
yeah. Ugh. Um, but yeah, no, the good thing about QSFPs and QSFP DDs is that you should be able to put a QSFP into a
Mhm,
QSFP DD port. You can't go the other way around though, because the tab sticks out too far. So,
mhm.
so yeah, while I actually have a handful of QSFP DD modules lying around, like I got one right here, I don't have much I can install them in. Um, as I think
Right.
I guess I have a couple different boards that take QSFP DDs, but only a couple. Well, that'll be getting those things working is a problem for a different day. One step at a time. Yeah, I think I have a couple different, I think Intel Agilex boards that take QSFP TDs, including the I series one, which I thought I had over here, but maybe I put it over there. Anyway. All right. Does anyone else have any questions or comments? No? All right. Well, if nobody else has any questions or comments, then I guess we can adjourn for today. If anybody is interested in the Switch development, I guess Carlos is not here today, but he'll be here next week, hopefully, with some news on the Switch. So if you guys are interested in that, then tune in a week. Otherwise, we'll adjourn until what was the next one? April 2nd, I think.
Yep,
Yeah.
that's what you
All
said
right.
earlier.
Yeah, I'm just double checking. So I don't give people the wrong information.
Makes sense.
I put the wrong information in
Yeah.
the slides before a couple times. I'm like, wait a second. Definitely want to avoid that if possible.
Makes sense, yeah. So say hello to Carlos next week. I'm most likely on Embedded World then.
Yeah,
the
okay.
Trade show here. So yeah, can't join then.
Yeah. Well, have fun at the trade show.
Thanks. Yeah.
Are you just attending or are you presenting something? Or does MLE have a booth?
Yeah, MLE has a booth, sharing with trends. No, I will be running around, I guess, meeting some people. There is a lot of, it seems as if this is quite a big thing for all the embedded folks. So there is a lot of Intel, AMD, or now Altera and AMD and Lattice and other people running around there. Yeah. So
All right.
having a couple of chats done.
Yeah. That'll be good. All right. Well, sounds good. I guess have fun at the conference and we'll adjourn until next time.
Yeah, thanks. Have a good time.
All right.
Thanks.
And thanks for the good work, Alex.
Yeah. Thanks. All right.
Goodbye. Have a nice day.
I'll close this thing down then. See ya.